Hello, in this video we will be continuing talking about the van der Waals equation and the different various equations that have been developed and improved over time. Just to give a brief background of what I'm talking about here with the van der Waals equation, this here is the generic cubic equation of state, which is essentially an updated version that has been improved from the van der Waals equation that was originally created. But the same basic principles hold true here. Essentially, what the van der Waals equation is telling us is that in order to calculate pressure for a gas that's in a non-ideal state, we have to take into account here this B term here. And this B term takes into account that since the molecules in a non-ideal gas situation see each other, they have volumes themselves. So the volume will not only be the volume of the container, but we have to subtract the volume of the individual molecules themselves. So that is what this B term accounts for. And this other term here on the right, it accounts for the interactions between those molecules. Again, since they see each other, these interactions will cause a decrease in pressure. That is why this term here is subtracted. Now, specifically in this video, the equation of state that we're going to be talking about is known as the SRK equation of state. Now, this equation of state was created in 1972, and I'm not going to go into the exact basics of how it has improved from the van der Waals equation, but just know that it has made the equation more accurate over time. So what we're going to look at in this video is we're going to look at how to, first of all, calculate this generic cubic equation of state with the parameters for the SRK equation of state. And then we're going to plot that equation onto a pressure versus specific volume diagram with isothermic curves. Now you might be asking, well, what does a pressure versus specific volume graph look like with isothermic curves? Essentially, it looks something along the lines of this graph here that you see on the right. And this graph here, again, we have pressure on the y-axis, the specific volume on the x-axis, and we have temperature here held constant. So if we look at PV over nRT with N being constant, we have PT over RT. So if we want to solve for pressure here, or excuse me, we have PRT over V. So if we want to solve for pressure here, we have that pressure equals the R ideal gas constant times temperature over V. So that is how we get these curves here. Now, more specifically, if we want to look at a critical point of a substance, we can look at this area right here where these curves are sort of bending down a little bit and then coming back up in a curved-like motion. And what is happening here is if we plot this and we see here this line here, this pink line here, we know that this line here represents the critical point for that substance because we can draw a horizontal line here, which means the first derivative of that would be 0. And there's also an inflection point here, so the second derivative is also 0. So that is just a little bit of background of a pressure versus specific volume diagram with isothermic curves. So we'll go ahead, and what we're going to do here is we have to code in our equation here for the SRK equation, and then we're going to go ahead and make a plot with isothermic curves from that SRK equation. So the first thing that we have to do here is I'm going to have to define a function that will return our parameters for the SRK equation. Now, if you'll notice here, our parameters we have an A parameter, we have a B parameter, we have an epsilon parameter, and we have a sigma parameter. The volume and temperature we will supply later on. So we'll go something like call our function cubic A, B, E, S for our A, B, epsilon, and sigma parameters. And this, go ahead and put the colon there. And what we'll want to do here is we'll want to obviously return our parameters. So we can write that in already. We'll go A, B, epsilon, and sigma. Well, now you might ask, well, how do we go about calculating this A, B, epsilon, and sigma, the parameters for the SRK equation? Well, the SRK equation has its own specific parameters for it. So here you see them down below here. And we have expressions for our A parameter here and our B parameter. So essentially what we're going to do here is set this up and just essentially plug in all the data that we have for the SRK equation in order to get our parameters. So we'll scroll down here, and if we look at the SRK portion in the table here, we can just start plugging in our simple values. So first we'll start with our sigma. So obviously we have that as S. And we notice that for the SRK equation that is 1, and epsilon for the SRK equation is 0. Now, before we go any further, what I would like to do here at the beginning here is, since our A parameter here is dependent on temperature, we'll have to go ahead and make that supply that for our function to make that dependent on temperature, so that our A parameter is dependent on temperature. Okay, so now let's go ahead and we can look at our B parameter here first. So this B parameter is multiplied by, or equals, this expression here. So this is omega times the R, the ideal gas constant, times the critical temperature divided by the critical pressure. So what we can say here is that we'll first start with omega because we don't know what omega is. And we'll have to plug that in, but we have omega in this table down here for the SRK equation. So omega equals 0.08664. Okay? Now that we have omega, we can go ahead and try to calculate our B parameter here. So we'll say that B equals omega. Okay, and that is multiplied by R, the ideal gas constant, which I have already written in here with the as given data. So that'll be multiplied by the ideal gas constant, and then this here, the critical temperature. What I have done here is all this stuff up here that says clone and this link right here. Essentially, what I have here is some pre-coded code that will allow us to get various information about the substance that we're working with here. Now, the substance in this example that we want to work with is just simply water. So what I'm going to do here is I'll go in and add a line of code. And in order to access that data that will get us stuff like the critical temperature for water and the critical pressure for water, we'll call this variable P, and we'll have to access it. So our CHE, and this will be prop, and the substance that we'll want to call in will be water. So the water will be the substance that we want to get information from. So I'll go ahead and press Shift Enter there. And now, since we have this available to use in the pre-coded algorithm already, we can say that the ideal gas constant is multiplied here by Tc. And since we have our variable as P, we can do P dot Tc. And Tc is the variable name for the critical temperature in the pre-coded algorithm that I have brought in. So that'll be multiplied by Tc, and then this entire thing is divided by P dot Pc, again the critical pressure. Okay, so that is our B parameter. I didn't mean to do that. P dot Pc. Okay. Now what we can go ahead and look at is we can go ahead and look at our A parameter here. So if we scroll down, we notice that our A parameter here has some different variables, some different Greek, or not variables, but it has some different parameters in here that they're Greek letters. And it looks kind of ugly at first, but we can see if we scroll down that we do have expressions for these. So our psi here, we have an expression for this. And this term here, this alpha times the reduced temperature times this Greek letter, we have an expression for this as well. All we need to do is just go ahead and plug this in. It looks really ugly right now, but if we just go ahead and plug it in, we can then see where we're going and see what we still need to calculate. So if we go here, we can start with our psi. So this Greek letter here is called psi. So let's go psi. And for the SRK equation, psi is equal to 0.5 42748. So I'll go ahead and write that in. Okay. And this whole term here, okay, this alpha term, for the SRK equation, it is down here written as follows. So what we're going to do is we'll just hard code this in here. So we'll call this alpha, and we'll say here we have 1, and we'll have to add 0.480, and we will add 1.574. Now this Greek letter here, this that looks like a W, this is what is known as the eccentric factor. Now I'm not going to go into great detail on what this is, but we can extract this from the pre-written data that we have here for water, so we can get the eccentric factor for water. So what I'll do here is I'll multiply this by P dot W, which is the eccentric factor for water, and from here I will subtract. Go ahead and make that there so it just looks even. I'll go ahead here and subtract 0.176 and times the eccentric factor squared. So the times P dot W squared. Okay. And from here, we will be multiplying this by 1 minus TR. Now, what is TR? TR is what is known as the reduced temperature. And we have a definition for the reduced temperature here. The reduced temperature is just simply our temperature divided by the critical temperature of the substance that you're working with. So for any substance, the reduced temperature is the temperature minus its critical temperature. So we can do P dot Tc here, so temperature divided by critical temperature. And we can substitute this in. So we have Tr, and this is raised to the 1/2 power, so it goes 0.5. And here we'll see that our parentheses do match up, so hopefully that we're good there and we didn't make a mistake. And this entire expression here is raised to the 2nd power. Okay, so now that we have our alpha and our psi here, we can go ahead and calculate our A parameter. So we'll go ahead and say that A is equal to, and again, we're going to have to be careful with signs here, but we'll say A is equal to psi times alpha. Okay. And this will be multiplied by r squared. So I'm going to go ahead and put this in parentheses just because I get sometimes nervous with parentheses and not working out. So we'll go ahead and put r squared in parentheses there. And we'll go ahead and put our critical temperature in parentheses as well. So we'll multiply this by the critical temperature. So P dot Tc. Again, this is squared. So raise that to the 2nd power. Okay, and let's see here, so these match up, and this entire expression here will be divided by the critical pressure. So we'll do P dot Pc. Okay, so let's go ahead and move that down. Okay, so now we can go ahead and we can press Shift Enter here. Okay, and we can go ahead and write out our function here, so cubic ABES, to see if it works here. So we'll go ahead and supply value for temperature, so I'll just supply 300. And there we go. So here are our parameters, again, in order here. So we have our, they're in order here. So we have our A parameter, our B parameter, our epsilon, and our sigma. And we know that this makes sense because our epsilon and sigma here are both 0 and 1. And that is true for the SRK equation. So we're good to go there. Now what we'll need to do here, since we now have our parameters, if we scroll up here, now that we have our parameters, we can calculate this general cubic equation of state with the SRK parameters, obviously, and solve it for pressure. So what we'll do here is we'll define a function that will return our equation here. So we'll do something like cubic pressure. So again, this equation is equal to pressure. And we'll have to supply both volume and temperature here. We already have our, I'm pointing to this equation, but this is the simplified one down here. So we already have our parameters here, but we'll need to supply the volume and temperature. So we'll have our volume and temperature there. Okay. And what I'll go ahead and do here is I'll unpack our function that we had defined previously into our parameters. So I'll go a, b, epsilon, and sigma. This will equal our cubic a, b, e, s. So a, b, e, s. Okay, and again, this is dependent on temperature, so I'll add that in. And from here, what we'll have to do is just return our equation. And our equation here is RT, so RT divided by, RT divided by V minus B, okay? And from here we subtract A, and we will be dividing A by, let's see here. Yeah, we'll do double parentheses there. So we'll have V plus epsilon times the excluded volume, B. So we'll have V plus epsilon times the excluded volume, B. Okay. And this will be multiplied by V plus sigma times our excluded volume, which is B. Okay. So our parentheses match up there. We should be good to go. Okay. So we've gone ahead and now we have an expression for our cubic pressure here. So let's go ahead and we can write this out and supply our volume and temperature just to see if it runs okay and we get the correct values. Okay. So we'll go 1e to the negative third for our volume. And for our temperature, we'll just do 300 Kelvin again. Okay. So there you have it. Now we have been able to calculate the equation here for pressure using the parameters for the SRK equation of state. Now we can go ahead and make a plot of our data. So to plot our pressure, we will need to plot the pressure at different volumes and different temperatures. However, what we can do here, and I'll actually do this first, we'll just plot at one temperature to see what the plot looks like to make sure that it's correct before we go ahead and plot the rest of our isothermic temperature curves. So what we can say here is that we can evenly space out our volumes here. So we just do V equals NP dot length space. This will, again, evenly space out our volume values. So we can start from a volume, and I'll just plot this here just so we can see where we're going, so we can sort of navigate through to get the correct diagram for our pressure versus specific volume diagram here. So we'll start from a volume of just 0 and go to 300, and we'll go ahead and put in 300 points here. Now what we'll need to do here is we will need to set a temperature here. So we'll just set our single temperature equal to just 400 Kelvin. And here what we'll need to do is we will need to I'll go ahead and put in our function, so the pressure equation. And we'll just put that with our linear spaced volumes. And we'll go ahead and supply our temperature there and just see what we have here. And it looks like I have an error here. Let's see here. Oh, I spelled length space wrong. Okay. So I'll go ahead and see what this returns. So this will return us, again, an array with 300 different values. But we have an issue here. We see that we have this negative infinity here. And the reason that arises is because we have volume values here that are less than our B value. But we know that that can't be true because the denominator here cannot be 0. So what we're going to need to do is ensure that each of our volume values is always bigger than our B parameter. So what we can do here is we can say for our starting value here for our volume, we can say multiply it by 1.01 times b. So that is just slightly above um, our b parameter. And for our n term here, we can say, let's bring it to 1,000. So 1e to the third times our b parameter, again, so that's always above. Well, now we do run into the issue of, well, what is b again? Well, we calculated it up here. So I'll just go ahead and copy and paste it into this cell block here. So I'll move that down, just paste that in. And I'll go ahead and just hard code in omega here. And omega for the SRK equation, which we're working with here, again, is 0.08664. So 0.08664. Okay, get rid of this parentheses here. Go back up to our equation. Okay. So let's go ahead and see our points here. So these are our points. Let's go ahead and throw up a graph of this just so we can see what we're working with here. So if we do fig equals make subplots, okay, and we add a scatter plot. So fig dot add scatter, and our x-axis here will be equal to, again, our specific volume. If we look here at our pressure versus specific volume graph with isothermal curves, our x-axis is specific volume and our y-axis is pressure. So now for our pressure on the y-axis here, let's see. So for the pressure here, this is our pressure equation here. So I'll just go ahead and unpack this into the variable P. And we can go ahead and put that on our y-axis. So let's go ahead and just plot this and see what we're working with. So here is our initial plot. And what we notice here is that we have our values so far spaced out. What we need to do here is turn this into a logarithmic scale, which will sort of squeeze our values closer together so that we can see the data, I guess, that we're working with. So we'll go ahead and I can do fig dot update, and I'll update the x-axis, and I'll go ahead and change the type of the x-axis to log. Okay, so we're looking better here. You see how that changes the dynamic of the diagram. But what we'll need to do is we'll also need to change our y-axis here to a logarithmic scale. Now what we can do here is, instead of linearly spacing out our points here, what we can do is we can change this into log space, which will space them out in terms of log. And a problem that we have to be careful with here is that when we use log space, this will change our starting and ending values to the power of 10. So what we have to do here to ensure, we want to keep the same starting values. We do not want to change these values here. So what we need to do is, if we take the log base 10 of them, that will keep them the same since they are raised to the power of 10. So if we do np dot log 10, and that's of this value, and again over here the same thing for our ending, so np dot log 10. Okay, and I'll go ahead and I'll change this so that we have more points. So I'll change that to 500 points. Okay, so let's see what that does here. Okay, so we're looking better there. We're looking more like an isothermic curve. However, what we can see here is that our y-axis, it's really big. So I'm going to go ahead and change the range of the y-axis. So if I do fig dot update y-axis, and I give a new range for the y-axis. So I'll put negative 2e to the 8 and 2e to the 8. Keep it even there. Okay, so there we go. Now we're looking like we have a isothermal curve here. Let's go ahead and change the mode to markers just to make sure that our points are where we think they are. So I'll change the mode here to markers. Okay. Okay, yep, so that's what we thought here. So I'm going to go ahead and change this back to a line. Okay, so let's see here. Oh, I need lines here. Okay, so this is an isothermal curve here for our one temperature value that we provided. However, what we want to do here is we want to graph this for multiple temperature values. Now, in order to do that, what we need to do is set up a for loop for temperature so that we can constantly iterate new temperature values and plot them on this diagram. So what we can do here is I'll go ahead and move this fig.make subplots up so that it will be above the for loop that I'll put in. And I'll go ahead and erase our temperature here. And to add in a for loop, it's just for temperature, and we have to give a range for that temperature for the for loop to iterate. So we'll do for t in range. We'll start at 275, so 275 Kelvin. We'll go up to 800 Kelvin and space them by 25 Kelvin. And I'll have to put a colon because that's the format for loops in Python. And I'll put this indented under the for loop, and this also, the scatter plot needs to go under the for loop as well. Okay, so there we are. Now we have plotted many different curves, again running from 275 to 800 Kelvin. And here they are plotted isothermically. Now, what you may notice here, well, actually, before I talk about the navigation system of the naming over here, we can actually decrease this X domain here. We see that this is 0.001, so I'll go ahead and hard code that in because we're not really interested in our graph over on the right side here. So I'll go ahead and excuse me, I didn't mean to do that, but if I go up here and hard code this in here to -3, this will be 10 again because this is log space. It raises our values to the power of 10, so 10 to the -3 is 0.001. So let's just go ahead and make sure this works here. Yep, okay, so it lowered it squeezed together our x-axis. So now let's take a look at our naming system over here. In order to get these to correlate to the correct temperature value that they're plotted at, what we can do here is we can say name, and we can use an F string here. Now on the F string, we'll label them temperature, and to get the actual temperatures, if we use these squiggly brackets here, we can actually insert our values for temperature that we have calculated. So I'll go ahead and do that and put the Kelvin in there. Okay, so go ahead and make sure this works. So yep, there we go. Okay, so we have now plotted our pressure versus specific volume diagram with isothermal curves. Now, if we want to take a look here, just before I end the video here. So if we want to predict here by looking at this graph what the critical point would be, if we look here probably at the blue curve here, this would probably be close to the critical point because we have a horizontal line here and an inflection point. So there we have it. That'll wrap up this video. We have now calculated the cubic equation of state for the SRK equation of state, and then use that to plot pressure versus specific volume isothermal curves here in Python. So thank you for watching.